Hi everyone, how are you doing? Hello Ajay, hi Aditya, hello Devesh, hello Sumaya. Okay, so today we are going to study positive definite matrices. This is a topic of linear algebra. So let's just see that what are these matrices. Okay, so let's just directly jump to the topic itself. Okay. So before I talk about the positive definite matrices, you might already be knowing about the symmetric matrices, right? That what are the symmetric matrices? So symmetric matrices you might be knowing, and there are there is one property, one important property about the symmetric matrices, that if it is a real symmetric matrices, then there will be real eigenvalues, right? So a positive definite matrices is a real symmetric matrices with all positive eigenvalues. See, for the real symmetric matrices, you have real eigenvalues. But if I'm talking about positive definite matrices, then these are the real symmetric matrices only. But here the eigenvalues will be positive also. So note that if it's a real symmetric matrix, then all eigenvalues are real. So it makes sense to talk about them being positive or negative. So what is positive definite matrices? It is just a symmetric matrix which is having the positive eigenvalues, right? Okay. So for example, now it's not always easy to tell if the matrix is positive definite. So can you tell me, is this a matrix positive definite? I mean, just by looking at it, hard to tell just by looking at it, right? So, which means what you need to do, you need to find out the eigenvalues of this. Okay, just find out the eigenvalues of this. And we are not really interested in the eigenvalues. We are interested in the sign of eigenvalues, right? So, I can say that to tell whether this matrix to tell to tell if this matrix is positive definite or not, then what we need to do? We need to find out eigenvalues, right? Obviously, we can do it, but let's just see if there is some other way to tell if this matrix is positive definite or not, right? So by looking at it, I can't say I need to find out the eigenvalues. But let's just see if there is any other way, okay, to tell by looking at it. So one way to determine if a matrix A is positive definite is to calculate all eigenvalues and check if these eigenvalues are greater than zero. The problem with this approach is that calculating eigenvalues can be real pain, especially for the large matrices, right? If it is a large matrix, then finding out the eigenvalues is like huge task. Therefore, today we will learn some easier method to determine if a matrix A is a positive definite or not. Okay. So let's just see that how to determine given a matrix is positive definite or not. Okay. So I have already told you what a positive definite matrix is. So let me just reiterate it that positive definite, a matrix is positive definite if it is symmetric, okay, and all eigenvalues are positive. Then we call it positive definite. Now let's just see that how to identify that what are the positive definite matrices. Okay. So Tejas is asking that what is the significance of positive definite matrices? So we will see this in the optimization. So whenever we will be doing the optimization, you will get to know that why we need the positive definite matrices, right? It has not been discussed yet. So yeah, this is a good question that why these positive definite matrices are required, right? So for example, let me write motivation. Okay. So which means why we are studying positive definite matrices, right? So the answer to this question is that we will be studying something called as first order or second order optimality conditions in optimization. So basically we need to optimize multivariate functions, right? And there the positive definite matrices play a very significant role. So we will talk about it later on, but let me write it that we need to optimize multivariate functions, right? There we need this concept, right? Positive definite. Let me just write PD. Actually, popularly, this is called PD. So let me just write PD or maybe positive definite for now. Positive definite concept. So what do I mean by optimize? Basically, we need to find minima or maxima, right? Minima or maxima of multivariate function. So minima or maxima of multivariate function. So there we need to understand what is the positive definite matrices, right? Okay. So you will get to understand this when we are going for the optimization in the higher order. Then you will get to know that why we need this positive definite matrices, right? Okay, great. So now let's just continue with the definition. So the definition, I already told you that this is how the positive definite matrices are defined. Which means if a matrix is symmetric and all eigenvalues are positive, then we say the matrix is positive definite. Is this okay to everyone? Let me know. I mean, this is just a definition, okay? So what is the definition? Matrix has to be symmetric and all eigenvalues are positive. Cool. Okay. So, like given a matrix, can you tell me directly? I mean, we cannot actually. There is no method we can directly tell whether the matrix is positive definite, which means directly. Obviously, we just by looking at it, we can't tell. Okay, but there is a better ways instead of finding the eigenvalues. The question here is that are we really interested in finding all the eigenvalues, or we are just interested in the sign of the eigenvalue, right? It seems like we are just interested in the sign of the eigenvalue, right? So we are just interested to know sign of eigenvalues. Okay, not the eigenvalues by itself, right? Not the eigenvalues. So the absolute the values of the eigenvalues we don't need to know. We just need to know the sign of those eigenvalues. Okay. So this is the important observation that we can make from here. Okay. So actually, there is one property of the symmetric matrices. We are not going to prove it. Okay. I mean, we can prove it, but that's not required. So the property is that sign of the pivots in the symmetric matrices and the sign of the eigenvalues are same. Okay. So which means that if we know, like if we can convert that to a reduced form, okay, or maybe the equivalent form, if we can convert the matrix to the equivalent form, and then from that form, if we know the sign of the pivot, then we know the sign of the eigenvalues. For example, for example, the number of positive eigenvalues, okay, will be the same as number of the positive pivots. Number of negative eigenvalues will be same as number of negative pivots. Number of zero eigenvalues will be same as number of zero pivots. This is true for symmetric matrices, okay. So this is true for symmetric matrices. Is this okay to everyone? I mean, this property we are not proving, but I'm just telling you this property. By the way, let's suppose that there is some matrix given to me. Okay. Suppose this is a matrix which is given to me. Now, suppose if I want to find the eigenvalues of this matrix, can I first, have the row equivalent form of this? So, for example, can I just say that, okay, maybe this R2 can be replaced by R2 minus, let's suppose R2 minus 2R1, right? 2R1. Then it will be 1, 2. And then if we just replace it, it will be 0. And 2 into this is 4. So then minus 3, right? So can I say that eigenvalues of this matrix is 1 and minus 3 because the diagonal matrix has eigenvalues on the diagonal. Can I say? Tell me. Can I apply this row elementary row operations on the matrix for which I want to find the eigenvalues. I mean, if I want to find out the eigenvalues, can I apply this elementary row operations? What do you guys think? So what I'm saying here is that suppose I want to know eigenvalues of this. Can I say that eigenvalues of this matrix is 1 and minus 3? So the answer is no. Okay. So answer is no. So we cannot say basically if you want to find out the eigenvalues, then you cannot apply this row operations. Okay. Which means if you want to find out the eigenvalues, then if you see if you want to find out the, let's suppose, system of linear equation, then this row operation makes sense. If you want to find out, let's suppose, determinant, okay, maybe see here I cannot apply row operations, but can I apply here? Suppose I want to find out the determinant of this. Okay, I do this. I want to find out determinant of this. Can I apply row operations here? Yes. So in the determinant I can apply. Okay. And if I want to find out the determinant, okay, this is a different matrix. This is a different matrix basically. These two matrices are not same. This is A minus lambda I, right? These two matrices are not same. So I'm not finding out the determinant of A. I want to find out the determinant of A minus lambda I. So I can apply row operations here, but I cannot apply row operations on A. Understood? So the answer is no. Okay. So we can apply row operations here. So elementary row operations are applicable only to the matrices for which I want to find out either the determinant or the system of linear equations. If you want to find out the eigenvalues, then it is wrong method that you are first applying the elementary row operations. Okay, so the eigenvalues of this particular matrix are not 1 and minus 3. I mean, this might be the coincidence. The eigenvalues are 1 and minus 3, but in general it is not 1 and minus 3. Okay. Now tell me, is this a symmetric matrix? Is this a symmetric matrix? Is this matrix a symmetric matrix? Yes, right? This matrix is a symmetric matrix. So I can say that this, I'm talking about this matrix. So this is a symmetric matrix. If this is a symmetric matrix, then can I know the signs of the eigenvalues by looking at its row echelon form? Yes. So you can tell me that one eigenvalue. Now you can tell me, because this is symmetric matrix, so I can infer from infer from that one eigenvalue is positive, other eigenvalue is negative. Okay, is this fine to everyone? Great. So one eigenvalue is positive, other eigenvalue is negative. This is what we can infer given this matrix and given this row echelon form. Understood? So so basically, given any symmetric matrix, I can convert that to a row echelon form, and from there I can basically understand whether the eigenvalues are positive or negative. Okay. Okay. So Ajay is asking, the multiplying a scalar is also valid row operation. If we multiply minus one again, we lose sign. So I mean, number of the eigenvalues you can at least get that one of the eigenvalue is positive and one of the other eigenvalue is negative. If you apply minus one, okay. Yeah. So here in this case, basically, yes, I got a point. So here in this case, like we will be just restricting ourselves to these kind of row operations only, right? So let's not change the sign of the pivot, which means that let's not multiply by the negative scalars. Okay. Okay. So now let's just read this paragraph that what they're saying. The thing is that there is a lot of other equivalent ways to define a positive definite matrices. One equivalent definition can be derived using the fact that for the symmetric matrices, the sign of the pivots are the sign of the eigenvalues. So for example, if 4 cross 4 matrix has 3 positive pivots and 1 negative pivot, it will have three positive eigenvalues and one negative eigenvalue. Okay. So now I can say, I can reiterate my definition of positive definite matrices like this: that a matrix is positive definite if it's symmetric, and instead of saying all its eigenvalues are positive, I can say all its pivots are positive. Okay. All its pivots are positive instead of saying eigenvalues are positive. So, for example, uh, given this matrix, the pivots are 1 and minus 3, right? If we perform elimination, subtract 2 into, if we perform this kind of elimination, then the pivots that we are getting is 1 and minus 3. So what we can infer from here, the pivots are 1 and minus 3. In particular, one of the pivot is minus 3, and so the matrix is not positive definite. Why? Because one of the eigenvalue will be negative. Okay. So, were we to calculate eigenvalues, we will see, I mean, you can calculate the eigenvalues, and then eigenvalues will come out to be 3 and minus 1. It is just a coincidence that eigenvalues are just, almost similar to the pivot, but it need not to be. I mean, here this is pivot is 1 and eigenvalue is coming out to be minus 1. If pivot is minus 3, eigenvalue is coming out to be 3. Anyway, like we are not interested in even calculating eigenvalues. Okay. So let's not even worry about the eigenvalues. Whatever the eigenvalue, let's not even worry about it. Understood? So tell me, given this pivot, can you tell me whether this matrix is positive definite or not? Yes, this matrix is not positive definite, right? This matrix is not positive definite. Okay. Now, basically, we have seen two ways, right? To basically understand whether the matrix is positive definite or not. How we can test using the eigenvalues, or maybe we can test using the pivots. But there are other ways also. Okay, two more ways. For example, if you know that all the n upper left determinants, or it is called principal determinants, right? N principal determinants. For example, if this is, let's suppose, 3 cross 3, then how many principal determinants you have? 3. This is one. I mean, you will take determinant of this element only. This is the second. 2 cross 2. This is 1, 3 cross 3. Okay. So, upper left, which means this is first left, second left, and this is third. So, basically, for n cross n, there will be n upper left or n principal determinants. Okay. So, we call it principal determinants. So what they are saying, that either you know that all eigenvalues are positive, or okay, this is just like or you know that all pivots are positive, then you can say the matrix is positive definite, or you know that all principal determinants are positive, okay, then you can say matrix is positive definite, or you know that there is a condition which is x transpose ax is greater than 0 for all x, which means you can take any vector x and then it is satisfying this condition for the matrix A, then also you can say it is positive definite. So basically, we will see the example and then you will get to understand, okay, that what I'm trying to say. But there are multiple ways where this positive definites are can be tested basically, okay. Now, all of these definitions are equivalent to each other, which means that if the matrix is having all eigenvalues are positive, symmetric matrix, okay, I'm talking about the symmetric matrix, then it implies that all pivots are positive. If all pivots are positive, then it implies, and it is by implication, that all principal determinants are positive. And if that is the case, then this condition also gets satisfied, okay. So again, there's a long proof of these things, but it is not required. So I have just skipped those. Okay, just complicated proofs are there that all of these conditions are actually equivalent to each other. Now let's just try to understand these conditions. That what do I mean to say that, right? So suppose in this question they're asking, is the following matrix positive definite or not? Okay. So let's just see if we can answer this question. So one way to answer this question is using the pivot. Another way to answer this question using the eigenvalues. Okay. And there are multiple ways, as I told you. And let's just use the third way here, which is finding out the n principal determinants. So you can say that, okay, this is positive. First determinant is positive. This is 4 minus 1. This is 3, which is also positive, right? So this is positive. This is positive. And if you find out determinant of whole thing, then also it is going to be, let's suppose, 4. So all of this are positive, so that's why it is positive definite. Is this okay to everyone? Okay, this is like one of the test. Which number test? So if I just number these tests, this is the third number test we have applied. Okay. Now let's just see this last test, that how to apply this last test. For example, if they're asking whether this matrix is positive definite or not, okay, so you can apply any test. By the way, by applying the test of determinant, what you can say, this is positive, and then this is 9 minus 1, this is also positive. So it is positive definite, right? Right. So, yeah, Sumay is asking, basically, we need to find the principal diagonal elements. No, no, you need to find out the determinants. Okay, this is first determinant, second determinant, like that, right? Okay, so this is definitely PD. Okay, this matrix is PD. But let's just use, or let's just see that how to classify this matrix is PD or not using the fourth condition. Okay, let's just try to understand the fourth condition also. So what does this fourth condition says? That if the matrix is said to be positive definite, then it has to satisfy this condition for all x. Okay, for all x. Obviously x cannot be 0, otherwise it will be 0. Then I mean, this is a trivial condition, that accept x equal to 0. But yeah, for all x it has to be satisfied, right? X transpose ax. So let's just check whether the x transpose ax is getting satisfied for all x or not in this case. Okay, so in the solution, actually they have found out the eigenvalues. These are positive. This is the first test. So you can say, okay, this is PD, positive definite, right? Again, they have applied the second test, which means they are saying, okay, let's just find out the pivots. So these are the two pivots. So using which you can say this is PD. You can find out determinants also. Using this you can say it is PD. Let's just see the fourth test. Okay, so the fourth test is saying that you multiply any vector x transpose ax, right? So it is x transpose ax. If you do this, then it will be some quadratic form. Okay, this is a quadratic form in the x1 x2. So basically here you can see that it like if you rewrite it, then it will be x1 plus x2 whole square, okay, plus 2 into x1 square plus x2 square. So basically, if you open this up, it is x1 square plus x2 square plus 2x1 x2, right? And then there is 2 into x1 square plus x2 square will get remain. So basically, the like this expression and this expression both are equivalent. Now tell me, is this expression always greater than 0 for any x? The answer is yes, right? Obviously, x is not 0. Okay, I'm trivially saying that x is not 0. So if you put any x, then since this is a square, these are also square terms. So obviously, it is positive. Is this okay to everyone? Let me know that this expression is always positive. Okay, so Tejas is saying, can we take just one x? For example, x equal to 1. No, it is not. It is not about one x. You need to test it for all the x. Okay, for x equal to 1, maybe it is greater than 0. But what if it is less than 0 for let's suppose x equal to -1. So we need to test for all the x. That is where this condition is important. Okay. So this fourth test is actually quite significant in our optimization. Okay, in calculus, we will see that this fourth test is actually quite significant, which means we will be using this fourth test in the calculus. But other test seems easier to check, but this fourth test is also significant. Okay, which means in the calculus we will see that x transpose ax. This form we will be using to say that okay, this matrix is PD or not, right? Anyway, like we will see this later on, but for now, is this understood that how to check for fourth test? You can just multiply x transpose ax, and then you can check whether this quantity is always greater than 0 or not. Okay, cool. So basically we have seen that this is a positive definite matrix, and what they're saying in this line, they are saying that any one of the above test is sufficient. Okay, so see here, it is not that you need to check for all the test, anyone. Okay, any one of the above test is sufficient to check whether a matrix is positive definite or not. Is this okay to everyone? So you don't need to check for all the tests, obviously. Just any one of them will work. Now just tell me, if a matrix is positive definite, then A inverse will also be positive definite. What do you think? So these true false questions can be, you can think about in terms of the eigenvalues. If let's suppose all the eigenvalues lambdas are greater than 0, then what do you think? 1 upon lambdas will be greater than 0? If let's suppose lambda is greater than 0, can you say 1 upon lambda I is also greater than 0? Yes, right? So that's why you can say that this is true. Okay. So this is true. Why? Because if these are the eigenvalues of A inverse, then I can say these are also greater than 0. Easy question, right? Okay, so Tejas is saying that can we say that A inverse is symmetric? Yes, we can say it, right? If A is symmetric, then A inverse will be symmetric. So you can probably, understand this with a uh, like you can have this eigenvalue decomposition, okay, by which you can understand that A inverse will also be symmetric. If let's suppose A can be written as, you know some, let's suppose Q diagonal Q transpose, then A inverse will be just almost the same thing, right? Q inverse. So basically this Q transpose inverse will be just Q if this is Q is orthonormal and this is diagonal inverse, okay, and this is Q transpose again, okay, something like that. Okay, you can use some of these properties. Yeah, so Ajay is also giving you some other property. He's saying that we can prove like this, okay, using the simple identity that A inverse is also symmetric. So A inverse is also symmetric. Okay, let's just see this. If A and B are positive definite matrices, then A plus B will also be the positive definite matrix. Okay, you are saying yes. What is the reason of that? So how you are saying yes here? No, eigenvalue of A plus B, is this 100% sure that it will be lambda? If this the eigenvalue of this is lambda, eigenvalue of this is mu. Can we 100% say that it is the eigenvalue of this is lambda plus mu? I think it is need not to be true, right? Why? Because the eigenvectors may not match, which means if this is Ax equal to lambda x, then it might be by. Okay, if it is bx equal to, let's suppose, mu x only, then yeah, a plus b equal to a plus b into x, then it is okay that it is lambda plus mu into x, right? But the problem here is that this x may not be matching. Okay, this x may not be matching, which means if the eigenvector of a is x, then it need not to be the case that eigenvector of b is also x. Okay, that's why this addition may not even make sense. Yes, so we can use the quadratic form here. Okay, so have you understood what I'm saying here? So the eigenvector of b need not to be eigenvector of b need not to be x. Okay, so then how to solve this question? See, if I'm saying that A is positive definite matrix, then it means I'm saying that X transpose AX is greater than 0 for all X. I'm also saying, by the way, this is a scalar, okay? This X transpose AX is a scalar number. Okay. Why? Because this is a vector, right? AX is a vector, and then X transpose means some row vector into column vector, then this will be the scalar. Okay. If this is greater than 0 for all X, and then if I say, let's suppose X transpose BX, it is also greater than 0 for all X, right? Can I say A plus B, X transpose A plus BX is also greater than 0 for all X using these two? Yes, right. Why? Because see here, this is X transpose AX plus X transpose BX, right? If this quantity is greater than 0, this quantity is greater than 0, then obviously the combine of this will be greater than 0, right? Okay, if this is greater than 0, I know this because this is positive definite. This is greater than 0, I know this because this is also positive definite. So I can definitely say that, the addition of two positive numbers will be positive only. Okay, so basically, I want to check whether this is greater than 0 or not. So I know this is greater than 0 for all x, right? For all x. This is also greater than 0 for all x, right? Okay. So you can say this is also greater than 0. I hope you understood. This is easy to understand, right? Okay. Yes, eigenvalues will also be, if this is positive definite, then eigenvalue of a plus b will be greater than 0. Yes, that is a good observation. Okay. Now, we have seen positive definite and we have seen these conditions, right? That these are the four conditions. There is one more definition, which is basically just a follow-up definition, which is called positive semi-definite or PSD. Okay, positive semi-definite, PSD. So PSD says that we will call a matrix A to be positive semi-definite. Again, this has to be symmetric. It is just that they are allowing zero also. Okay. So instead of saying greater than zero, here it was a greater than zero. Positive means greater than zero. Positive means greater than zero. Positive means greater than zero. This is greater than zero. So instead of everywhere saying greater than zero, they are here saying greater than equal to zero, greater than equal to zero, greater than equal to zero, greater than equal to zero. Okay. That's the only difference. Okay. So all eigenvalues are greater than equal to zero. All pivots are greater than equal to zero. All the principal determinants are greater than equal to 0. Okay, or maybe x transpose x is greater than equal to 0, right? If you have greater than, I mean, if you are including 0, then this is called positive semi-definite or PSD. Okay. So for example, let's suppose this is a question which I've taken from IIT Madras. So what they are saying, find whether this is positive semi-definite or not. So you can apply any test. Let's just quickly apply all of these tests, right? So let's just apply the first test. If you find out the eigenvalues, these are like these eigenvalues. Using this test, can you say it is a positive definite? Can you say it is positive definite? No, right? It is positive semi-definite. Like, because it is having zero, so it is not positive definite. It is positive semi-definite. But positive. Okay. So which is called PSD, right? So now from now on, we can use the short form. It is called PSD, positive semi-definite. Now, if you use the second test where you will be finding the pivot, if you find the pivot, then the pivots are 0, oh, sorry, 2, 3 by 2, and 0. So here, one of the pivot is missing, right? One of the pivot is equal to 0. Then you can say it is positive semi-definite, right? It is not positive definite. From here also, it is the conclusion that it is not positive definite. It is positive semi-definite, which means it is not PD, it is PSD. You can also find out the determinant, and then you will say that, okay, if you find out the determinant of this whole thing, then one of the determinant, which is the determinant of this complete matrix, is actually 0. So you can say that that one of the determinant is 0, then it is positive semi-definite, and all other determinants has to be positive actually. Okay, if let's suppose any one of the determinant is negative, then one of the determinant is negative, one of the determinant is positive, one of the determinant is 0, then can you say anything? Then we cannot say. Okay, then we cannot say, right? This is neither PD nor PSD. Okay, this is neither PD nor PSD. If one of the determinant is less than 0, one of the determinant is greater than 0, one of the determinant, let's suppose, equal to 0, something like this, right? Then it is neither PD nor PSD. Okay, so obviously matrix need not to be PD or PSD. It may be neither of them. Okay, it may be neither of them. Now let's just apply the fourth test. If you apply the fourth test, X transpose AX, if you let's suppose find out, then you will be actually getting this, which is greater than equal to 0, right? Is it always greater than 0? No, right? It can be greater than equal to 0, right? It can be greater than equal to 0 also. Understood? So it can be 0 if x1, x2, x3 are equal. So that's why it is positive semi-definite. So again, they are saying that any one of the above tests is sufficient to check whether a matrix is positive semi-definite or not. Okay. So any one of them. You don't need to apply all the tests. It is just for the sake of example that we are applying all the tests, right? Now, let's just see this example. What they're saying. For what numbers b is the following matrix positive semi-definite? Okay. So you need to find out the value of b such that the matrix is positive semi-definite. This question I have taken from University of Otaha. So how to solve this? You can use maybe the eigenvalues or maybe the pivot or whatever, right? Maybe the determinant also. So this is positive, this is okay. So maybe you can find out the determinant, right? So this is greater than or equal to 0, right? 4 minus 1, which is 3. I think this was the example we have done, right? Here b was not there. So anyway, so basically this complete determinant has to be greater than or equal to 0, right? So let's just find out the complete determinant. Maybe it will be easier. So if we find out the complete determinant, it is coming out to be a minus 2b square plus 2b plus 4. It has to be greater than or equal to 0. So you can say from here b square minus b minus 2 is less than or equal to 0. If you just factor it, it will be b minus 2 into b plus 1. It is less than or equal to 0. So what does this mean? That b, see, if it is less than or equal to 0, it means, see, this is minus 1, this is 2. So lesser than minus 1, it will be positive, then negative, and then positive. So it is negative in this range, right? Minus 1 and 2. So if b is from minus 1 and 2, it will be less than or equal to 0. Okay. So in this range, if you put b, it will be PHD. Understood? So you can put any value in this range and the matrix will be PHD only. Okay. So these are the simple definitions of PD and PhD. Now, there is one more small topic, which is called quadratic form. Okay, it is a follow-up topic. It is easy and small. So we have completed the discussion about the PD or PhD matrices. It is just that we need to know that what is the definition, right? So which means if the eigenvalues are positive, or maybe the pivots are positive, or like I'm talking about the PD, or maybe X transpose AX is greater than 0, or what is the fourth condition? Like the principal determinants, right, are positive. So this is called PD, right? There is also, I mean, like we don't need it, but there is also something called as negative definite and negative semi-definite, right? So, and also negative semi-definite. So whatever the fourth conditions we have written, okay, instead of positive, if this is negative, then we will say it is negative definite. For example, if let's suppose, if I say that all eigenvalues are less than 0, right? Or I say, what was the second condition? Pivots, right? Pivots are less than 0, all pivots, right? All eigenvalues. Or I can say all principal determinants are less than 0. Or I can say X transpose AX is less than 0 for all X. Okay. So this is the definition of negative definite. I mean, this is just a follow-up definition. Here, instead of positive, they have negative. That's all. Obviously, if we have negative definite, then you can also have the definition for negative. What is remaining? Semi-definite, right? So here, in all those conditions, okay, you will be having less than equal to 0. That's the only difference. So here you will be having less than equal to 0, less than equal to 0, less than equal to 0, less than equal to 0. Okay. So you can have positive definite, you can have positive semi-definite, you can have negative definite, you can have negative semi-definite. Now it is not necessary for a matrix to be either of this. Okay. So which means, let's suppose there's a matrix. Okay. For example, it is like I can say it is not necessary for a matrix to be either of PD, PhD, Okay. So generally this ND and these things, like no one use this negative definite and these things much. So if you want, I can write it. But let me write it negative definite or negative semi-definite. So for example, if we have a matrix, let's suppose, okay, something like this, where let's suppose one pivot is 2, another pivot is -3, another pivot is, let's suppose, okay, once you have 2 and -3, then the game is over, right? So maybe you can have 2 cross 2 matrix even. So this matrix, tell me, are all pivots are positive? No. Are all pivots are negative? No. So this matrix is neither of this, right? This matrix, neither of any above. Okay. It is not necessary, obviously, for a matrix to fall in these categories. Okay. Cool. So now let's just see a follow-up topic, which is called quadratic form, right? Okay, Tejas is asking, so what about zero matrix? So I think zero matrix, you can put it in the positive semi-definite or maybe negative semi-definite also, because X transpose AX is actually greater than or equal to zero also and less than or equal to zero also, right? Or maybe the pivots are all pivots are basically, you can say, like, or the eigenvalues, you can say, maybe see here the pivots you can see. Actually, there is no pivot here. So okay, so let's not apply that pivot definition because there is no pivot here. So you can say that, okay, X transpose AX, right? You can apply this definition is actually greater than equal to zero or less than equal to zero also. So you can put it in the positive semi-definite or the negative semi-definite. Okay. Now let's see one more definition, which is called quadratic form. So what is this quadratic form? So by the way, this quadratic form is a part of the GATE DA official linear algebra syllabus. So there's a topic called quadratic forms that is written there. Okay. So let's just see this. That what is this quadratic form? So for example, if we have any this linear kind of equation, then we call it as a linear form or a linear function. For example, this is a linear function. Okay. So A transpose B, C transpose X, these are the linear functions. So we can also have the quadratic functions where these x will be in the square or maybe the pair, right? Which means x1, x2 or something like that, right? So basically two x1, x2, x3, x4 like this will be in the pair, or maybe these are the square terms. Then these are called quadratic forms. Okay. So for example, this is a quadratic form, this is a quadratic form, this is a quadratic form. So these are the quadratic forms, right? So where f is a you can say f is a function which is taking a vector and finally it is giving you a scalar. Okay. So this scalar is in the quadratic form, you can say. Okay. The parametric form is basically the quadratic form. Okay. Now, so okay. So May is saying please repeat. No, this is just the quadratic forms. If it is in a square format, then I'm just saying it is a quadratic form. Okay. So don't worry, you will get to understand that what do I mean by that. So suppose f is a function which is a quadratic, then what we can do, we can represent this f just like x transpose ax. Okay. So which means if this is a quadratic form, then you can represent this as x transpose ax. Okay. Maybe here you can say very simply that x is nothing but x1, a is nothing but identity matrix, and this x is nothing but x1 only, right? So maybe you can represent this like x transpose x1. Okay, here A is the identity matrix. Similarly, you can represent this also as X transpose AX. Okay, so any quadratic form you can represent as X transpose X, right? For example, this can be represented. We will see that how, but this can be represented something like this: x1, x2. This matrix A, and then sorry, this X transpose. So this will be x1 x2 like this, and there's a matrix A which is something, and then x1 x2. Okay. So what is this matrix A? We will see that how to find out this matrix A. But for now, if I just plug in this matrix A, okay, it will be little complicated for you to understand. But yeah, it is something like this. Okay. So this matrix A, if you actually multiply all of this, you will be getting this. Okay. So we will see that how to find out this matrix A. But yeah, given any quadratic form, you can represent this any quadratic form in the x transpose Ax. For example, you can also represent this in the x transpose Ax, where x will be x1 x2 x3. A will be some matrix 3 by 3 matrix, and then this will be x1 x2 x3. So you can also represent this. And how to find out this matrix A, we will see it. But for now, let me just fill these values. X1 x2 x1 x3. Okay. So this will be the values. Okay. We will see that how to fill these values. But yeah, any quadratic form can be represented like x transpose X. Is this okay to everyone? Okay. So what is that they are saying? That if we are having the quadratic form, then okay, any equation of the quadratic form can be written in the form of x transpose Ax. Okay, where A is a symmetric matrix. See, let's just understand this carefully. See what they are saying, that this A is a symmetric matrix, and if you observe in all of these examples, I have written this A is a symmetric matrix, right? This A is a symmetric matrix. Now, obviously, there are possible ways we will see that if you want, you can represent this x transpose X where A is not symmetric. Okay. For example, if I just tell you the example that you can represent this 2 as like this. Okay. So which means this is 2, 3, maybe -1 and 0. So if you multiply all of this, then also you will be getting the same quadratic. Is this a symmetric matrix? Tell me. If this is a symmetric matrix, then the answer is no, right? So basically what I'm saying, just understand this carefully, that you will be representing any quadratic form like x transpose X. Okay. Here, a a if you want, you can make it symmetric. I mean, we will see how. Okay, we will see how. But if you want, you can choose to put the value such that A is symmetric. You can choose to put a value such that A is not symmetric. Okay, but that's not the point of discussion. The point of discussion is that if it is a quadratic, then we always have a matrix such that we can always put the value in such a way that we can always make A as a symmetric. Are you getting my point? See, what I'm saying, that you can put this A either as a symmetric or as a non-symmetric. That's fine. But let's not worry about the case where we can put A as a non-symmetric. We are worrying about the case, or we are considering about the case that we can put A as a symmetric. Okay. No, it is if and only if, in the sense that if this is a quadratic form, then you can put as x transpose Ax, where A is symmetric, or if x transpose Ax is given, then this x transpose Ax is a quadratic form. So basically what I'm saying, that given any quadratic form, you can represent that quadratic form as x transpose Ax. Now here A you can choose in such a way that A is symmetric. Understood? Can you choose A in such a way that A is not symmetric? Tell me. Yes, yes, we can choose A in such a way that A is not symmetric. That's also fine. Okay. But are we considering that case, or we are interested in that case? No. Okay. So basically what I'm saying, that given any quadratic form, okay. So let me just tell you, there are almost, like I can say infinite possible ways to represent this as a quadratic form. Let me just tell you quickly few ways. For example, x1 x2. Okay. So let me put the values, and then you can quickly verify whether this is giving you the desired uh, result or not. Okay. There are many ways. Okay. So for example, let's suppose I have these ways. For example, this is one of the ways, you can put 2 here, you can put 3 here, you can put minus 1 by 2 here, you can put minus 1 by 2 here. Here you can put 2, here you can put 3, you can put minus 1 here, you can put 0 here. Here you can put 3, you can put minus 1 here, 3, 0. You, you can multiply these matrices. Okay, you can multiply these matrices. You will see this is also leading to this is also leading to this is also leading to this. Okay, is this fine to everyone? How to find out these coefficients? It's easy, actually, extremely easy. As you can see that I can write it very quickly, or it's very easy. I will tell you. Okay, in just a minute I will tell you. Okay, so all of this are leading to the same quadratic form. Is this fine? Is this a symmetric matrix? Yes. Symmetric. Yes. Is this a symmetric? No. Is this a symmetric? No. Okay. So basically you can represent this quadratic form as X transpose X, where you have choice to make A symmetric or A is not symmetric. Okay. That's fine. But we are not interested in these cases where A is not symmetric. Got it? So it's just like that we are not interested. It's not about the case that we can represent or we cannot represent. You can definitely represent. It's just like that we are not interested. Why? Because symmetric matrices anyway has good properties. Okay. So if we have choice of representing as a symmetric matrices, then we will be doing it, right? Now, if you can represent this as symmetric matrix, then basically there will be just unique choice. So let me just tell you the coefficients, how to find out the coefficients. See, this is this is like you can consider x1, x1. Okay, this is basically you can consider like this. See, this is x1, this is x1, x1, x2, x2. Okay. So which means this is x, sorry, x1, x2, x1, x2. Okay. So basically this is a coefficient of x1 into x1. So which means here you will be writing definitely 2. Okay. There is no choice here. You will writing 2 here because x1 into x2 has two coefficient. x1 square has coefficient as 2, right? Similarly, x2 square has coefficient as 3. So x2 square has coefficient of 3. So here you don't have any choice. What about this? This is coefficient of x1 into x2. This is coefficient of x2 into x1, right? So basically, this x1 into x2 coefficient, you can split it into two parts. What is this coefficient? Minus 1. You can split this minus 1 into two parts, such that one of the part you will be writing here, another part you will be writing here. So you can split this minus 1 into minus 1 by 2 and minus 1 by 2, which means minus 1 by 2 here and minus 1 by 2 here. This is one choice. You can split it minus 1, 0, right? Minus 1, 0, 0, minus 1, or whatever way you want, right? Or maybe any other way, maybe 3 minus 4 or like that, right? You can split it in any way, and you can put this coefficient because this is the coefficient of x1, x2. This is also coefficient of x1, x2. Both will be combinedly giving you this coefficient. Okay. So you need to put in such a way that summation of these two is minus 1. And obviously there are infinitely possible ways, right? But obviously this minus 1, if you want to split in the equal half, then there is just unique way, right? Just unique way. Because we want these two values to be same. So if you want to put in this just equal half, then there's just unique way. So which means if you want to represent this as a symmetric matrix, then there's just a unique representation. Okay. Little bit you might be getting what I'm trying to say. I mean, we will be having the examples. Let's just see. Okay. Let's just see. So basically, what I'm saying here that any quadratic form you can represent at X transpose X, okay, where A is a symmetric matrix and it is a unique symmetric matrix. It's not like that you have multiple forms of X transpose X where in all the forms this A is a symmetric matrix. Okay, so what they're saying that the matrix is uniquely determined by the quadratic form and it is called the symmetric matrix associated with the quadratic form. Okay. So you can have the quadratic form. You can represent this as a X transpose X, and where A is a symmetric matrix. And it is a unique symmetric matrix that is associated with the quadratic form. Anyway, let's just see the examples and you will get to understand. For example, if this is A, this is B, if you multiply, let's suppose this X transpose AX, okay? If you represent this A as a quadratic form, then it will be X transpose X, you can multiply, it will be like this, right? Or maybe directly also you can tell. How to tell directly? One means this is a coefficient of x1 square, this is a coefficient of x2 square. So you can directly write, okay? Or if you want, you can multiply. Okay. Similarly, this is a coefficient of, tell me quickly. This will be the coefficient of, if you just multiply all of this, x1 square, this is the coefficient of x2 square, this is a coefficient of x3 square. Now, if someone asks you, tell me the coefficient of, let's suppose x1, x2, then it will be x1, x2 minus 1 plus x2, x1 minus 1. So minus 2. Basically, you need to add all the coefficient of x1, x2. Okay. So minus 2. Okay. This is minuses here, minus 2. Understood? Similarly, if someone asks you, tell me the coefficient of x2, x3, then this is basically x2, x3. This is 1. And similarly, x3, x2. This is also 1. Right? So 2 into that x1, x2, x3. Understood? So either you can multiply or you can see that okay, we can infer the coefficients directly, right? Given this matrix, you can infer the coefficient directly, and obviously given this quadratic form, you can go here, or given this matrix, you can go here. Okay. So we will see the examples, but it is just the very first example. Understood? Now let's suppose they ask you compute the product X transpose AX when A is symmetric 2 cross 2 matrix. Okay. Suppose for this given A, you want to compute this product X transpose AX. How to do it? You can find out the product, but I mean you can multiply like this x1 x2 1 2 2 minus 1, okay, x2, sorry, x1 x2. Or maybe you can instead of multiplying, you can directly tell how. See, this 1 means this is x1 square, this minus 1 means minus x2 square, this is 4, right, plus 4 into x1 x2. Yes, all of you are correct. So this is x1 square minus x2 square plus 4 into x1 x2. Understood? Okay, great. Now let's just move to the next question. So see here, they multiplied and they have got the same answer. Okay. So if you multiply, I think they first multiplied these two, which is fine. And then you multiply these two. Okay. Again, they're asking, by the way, this question I have taken, if I remember correctly, most of the material of this particular class I have taken from David Seeley. Okay, David Seeley is one of the book you might be knowing. If you don't know, that's fine. There is a one standard book, David Seeley. Okay. So let's see that how to find out this. The quadratic form corresponding to this particular matrix. You can directly write, right. What is the answer? 4x1 square plus 3x2 square. Here, what is the answer? 3x1 square plus 7x2 square minus 4x1 x2. Okay. Or if you want, you can multiply. I think in this particular example, they multiplied these two first, right? And then they multiplied this x1 x2. That's fine. Okay. So if you want, you can multiply, or if you want, you can tell the answer directly. For example, let's suppose this is qx, which is given. And now they're asking, find out the qx for x equal to these values. So they're asking you to find out the value of the quadratic, final value of the scalar. Okay. If x is this, or x is this, or x is this, like that, right? So I think that's easy. You can directly put the values and you can find out the value of the scalar, right? For example, if you do this, then 28, 16 minus 20, these kind of answers you will be getting. Understood? You can just put these values here and you can get the answer. Okay. So now let's just see a reverse question, which means given the quadratic form, they're asking you to get the matrix A. Okay. I mean, we are interested in the symmetric matrix only. So can you tell me? x1, I think this is 5, x2 square 3, this is 2, right? This coefficient you can just divide by 2, x1, x2, which is minus 1 by 2, minus 1 by 2. So these coefficients always divide by 2, okay? So this is minus 1 by 2 here, then minus 1 by 2 here. Then this is x1, x3. So what is x1, x3? x1, x3 is not there. Okay, great. You people also got the answer. So basically x1, x3 is not there. You can just put 0, okay? If this is not there, 0, and x3, x1 also 0. Now these two entries are remaining. So what is x2 and x3? It is 8, just divide by 2, always divide by 2. So it is 4 and 4, right? Okay. So I hope this is okay to everyone, that how to find out the matrix also, right? Corresponding matrix also. Just a second. So by the way, this again, this question is also from David Seeley. Okay. I mean, that was presented this link also, but anyway, this is also from David Seeley. So this is your answer, right? I think the answer is matching. Okay, great. So always divide by 2. Okay. So whatever is the cross product, cross terms. So these are called actually cross terms. Okay. So for the cross term coefficients, just divide by 2 and then put at two places. Okay. Instead of just putting at one place, just divide by 2 the cross term products. Okay. For example, if they ask you to find out these matrices, I think you can do it, right? So let's not do it. I mean, you can do it and the answer is on the next page. So this is the answer that is on the next page. For the sake of practice, you can do it, right? Okay. So see here, symmetric matrices are useful but not essential for representing quadratic forms. Is this okay to everyone? What does this line saying? That these are useful, but it is not the only place or only the kind of matrices using which we can represent the quadratic forms. You can split in any way you want. Okay. For example, the quadratic forms can be written as, so this is okay. This is not a symmetric matrix, right? So they have split this 6 into 5 and 1. This is fine, right? So that's what they are saying, that where the coefficient 6 of the cross product term has been split as 5 plus 1 rather than 3 plus 3 as in the symmetric representation. Okay. So instead of dividing by 2, if you want, you can have any split. Okay. That's fine. So it is essential. Sorry, it is useful but not essential. Okay. It is useful but not essential. However, symmetric matrices are usually more convenient to work with, so it will always be understood that A is symmetric when we write in X transpose X. Okay, even if not stated explicitly. So even if they do not say that okay, this A is a symmetric matrix, it is understood that we can represent any quadratic form as a symmetric matrix here. Okay, we can choose to be a symmetric matrix, so we will be choosing the symmetric matrix only, even if it is not stated explicitly. Okay, this is so common that even if they do not say that it is a symmetric matrix, you can represent it as a symmetric matrix. Okay. Okay. Let me know what is the correct answer here. Find the symmetric matrices such that this qx equal to x transpose ax, where x is this 5, 1, and minus 5, minus 5, right? So I think A is the correct answer. Okay. This is the answer. Now, what they're saying, symmetrization of the matrix, the quadratic form can be represented, for example, by this, okay, using this, I mean, you can split what was the coefficient minus 10, okay. Minus 10 can be split at a minus 8, minus 2, or maybe minus 3, minus 7, or minus 5, minus 5, okay. So, and the last one is symmetric, okay. So this is about the symmetrization, right? So minus 10, you can split as minus 8, minus 2, or maybe you can split this minus 10 as minus 7, minus 3, or you can split this minus 10 as minus 5, minus 5. Yes. Okay. So you can find out the symmetric matrix, right? That's fine. Okay. In some cases, the quadratic forms are easier to work when there is no cross product. So basically, you can see that like these are the cross product, right? Cross product terms. So which means that x1, x2 like this. Okay. let's suppose let's suppose we are looking for the quadratic form where we are just having x1 square, x2 square, and x3 square. We don't have these terms, which means the corresponding matrix should be diagonal, right? The corresponding matrix should be diagonal because we don't want these things, right? The corresponding matrix should be diagonal. So which means if we are only looking for the quadratic forms where you can represent that quadratic form in such a way that the corresponding matrix is diagonal, then these cross product terms will not be appearing, right? So there's a text or there's a paragraph from David Seeley, chapter 7. I have taken it, right? So what they're saying, in some cases, quadratic forms are easier to use when they have no cross product term, right? So what does this mean? If we don't want any cross product term, then the corresponding matrix should be diagonal, right? So if we don't want, okay, understood. Now, interestingly, just see here that let's suppose that qx, okay, is basically, let's suppose you have qx, which is x transpose ax, and this A is a symmetric matrix, but it is not a diagonal matrix. Okay, then can I represent this as y transpose dy, which means these two should be equivalent, which means that x transpose ax, if I just choose this x in such a way that I just have some different representation of the x in such a way that finally I'm able to have this diagonal matrix inside, okay, or diagonal matrix in between, then I can say that basically I can represent the quadratic form in the form of the diagonal matrix also. So will it be possible for me? What do you think? So what will I do? See here that uh, you might remember eigenvalue decomposition, right? See, ax equal to lambda x, if x is eigenvector, do you remember? Obviously, right? So let's suppose instead of one eigenvector, I have whole matrix of eigenvector. Then if you remember, let me write it x lambda. Then you might remember this is u, okay, the whole eigen matrix of eigenvector, then u and then lambda, right? So here a, if you remember it again, u lambda u inverse, right? If A is a symmetric matrix, then basically this u will be like you can choose this u to be orthogonal, then u inverse will be u transpose only. So basically it is u lambda u transpose, okay, for the symmetric matrices. Do you remember this eigenvalue decomposition? Okay, so basically any any matrix A can be represented like this, right? So this A can be represented as, let's just represent this as P D P transpose. Okay. If this is a symmetric matrix, then you can represent using the eigenvalue decomposition. You can represent it as P D P transpose. Okay. So, so from here, what we can say, if you represent this as P D P transpose, then this will be X transpose P D P transpose X. Right. Now just assume this to be Y. Is this Y transpose? Which P is a orthogonal matrix. So what will the Y, if Y is P transpose X, then what is Y transpose? Tell me. It is, I think, X transpose P, right? So automatically this is Y transpose. So if you assume this to be Y, okay, then automatically this is Y transpose. So basically what I'm trying to say, that step one, what is the step one? put A equal to, suppose PD P transpose, right? Then we will be having QX as X transpose P D P transpose X. Okay. And what is step two? Step two will be that put Y equal to P transpose X. Then automatically this QX will be P transpose X transpose D P transpose X, right? Which is same as Y transpose D Y. So basically what I'm saying, if a quadratic form is given to you, okay, and there is a symmetric matrix, obviously we can have a symmetric matrix for the quadratic forms, right? Then what we will be doing, we will be basically saying that, okay, let's just do one thing. Instead of writing this as X transpose X, let me write it as Y transpose dy, which means you can say from here, you might remember the change of basis, right? You might remember change of basis things. So what is change of basis? Let's suppose X is in the standard basis, okay? Suppose E means standard basis, suppose. Then if you multiply with the, I mean, you can multiply the identity matrix, right? So basically identity, basically whatever is the basis, you just multiply with that basis, then the finally it will be the standard basis. You remember these kind of things? Okay. So what I'm saying that, okay, if you don't want to multiply, that's fine. I mean, I'm just saying that, okay, for any vector, if you multiply with their basis, if this is a standard basis, then you multiply with the standard, basis, you will be getting the whole thing in the standard basis. Okay, it is. If this is confusing, then let me just tell you that you can represent this x in some other basis. Okay, suppose x is in, maybe let's suppose the basis p, and then you can multiply with the matrix P, right? Then this whole thing in the standard basis. Okay. Now, what I'm saying that, if you observe here, then what I'm saying that you just do one thing, that this x in the basis of P will be what? P inverse x in the basis of standard basis, isn't it? Is this fine? Is this okay to everyone? That if you want to represent x in the basis of P, then you can just multiply P inverse there, and then you will be getting x in the basis of P, right? Now, suppose P is orthogonal matrix, then you can also say that, okay, let me just multiply by the P transpose. I mean, that's fine. You just multiply by the P or P inverse or P transpose, doesn't matter if this is orthogonal, right? So you can just multiply by the P transpose. Okay, so P transpose into X. Now, if you observe here, this is P transpose into X. So what I'm saying, that instead of saying that X is in the standard basis, let me do one thing. Let me just treat, okay, just it's just a way of seeing the things. Okay, so let me just view this quadratic form. Instead of viewing this in the standard basis, let me just view in the basis of P. If I view the quadratic form in the basis of P, right? If I change the basis of X to be, if I just represent this X to be, for example, this X will be, or maybe if I just replace by to be P transpose X, then I will be getting this. Okay. So here X is in the standard basis. And then here, this by, you can say by is the coordinates of X in the basis of P. Okay. If you have the coordinates of X in the basis of P, then basically this is the matrix of eigenvalues, right? I mean, this is a diagonal matrix will be the eigenvalues. So basically if you just represent this particular vector y, or sorry, particular vector x in the basis of P, then you can basically write it as by transpose, where what is the relationship between by and x? By is just x only, but in the basis of P. Okay, so I can say by just x only. Okay, in the basis of P, if you just represent this by, then what you can do, you can say that, okay, you can view this quadratic form as a diagonalization. Okay, basically you can have the diagonal matrix in between, okay, instead of just having the symmetric matrix. So let me just go over it. So basically, like this again, I have taken from David Seeley, chapter 7. So this is called change of variable in quadratic form. So for example, if you just put x equal to py, or maybe by equal to p inverse x, or maybe by equal to p transpose x, okay, which is also equal to, if p is orthogonal, then it is p transpose x, right? Or maybe x as py, okay, both are fine, in whatever way you want to represent it. So basically, I have used a diagonalization and I have shown you, but they are representing this x as py. Okay, basically they are just writing this x as py, and finally they will be getting the same thing. So let me just show you. Okay, let me just show you something. So using the example, let's just see. So for example, they are saying that given this quadratic form, represent this quadratic form in such a way that there is no cross product terms. Okay. I want to represent this quadratic form in such a way that there is no cross product terms, which means the corresponding matrix that I'm looking for should be the diagonal matrix, right? So how we can do it? You can just say that first find out the matrix A. Okay. What is the matrix A corresponding to it? What is the matrix A corresponding to it? 1, -5, -4, and -4, right? Is this fine to everyone? Now just find out P. Okay. P means, P is, if you remember from the diagonalization, P is a matrix of eigenvectors. Okay. So first eigenvector of A and the second eigenvector of A. So basically, if you find out the eigenvalues and eigenvectors, then this is basically P and this is D. Okay. This is P and this is D, which means D will be the diagonal matrix of eigenvalues and P is the matrix of eigenvectors. Do you remember this? That how to find out this P and D using the eigenvalue decomposition. Okay. So this is till now we have not done anything other than the eigenvalue decomposition, which means if I just consider this part, okay, if I just consider this part, we have just done the eigenvalue decomposition. In the sense, we found out the eigenvalues and eigenvectors. We found out what are the corresponding P and D. Now, now this is the eigenvalue decomposition. Okay, and from here, what we can do, we basically want to change. Okay, this x to, I mean, instead of writing x, I will be writing py. So basically, given this quadratic form, instead of writing this x transpose ax, I will be writing it as by transpose. So basically, it will be, instead of x, I will be writing py, and I will be writing it as by transpose dy. Okay. So D you already know, right? What is this D? D is the matrix of eigenvalues. So you will be having something like this. So which means let me just tell you further. So which means, let's suppose they give you, for example, let's suppose they give you some quadratic form which is this one, right? They give you qx, something like this. Suppose they say that find out qx for 2 minus 2. Okay. But using the diagonal form. So what is the first step? I will be converting this 2 minus 2, which is in the base standard basis. I will be converting that to y. Okay. In the basis of p. So convert. How to convert? if you remember that if something is in the standard basis and I want to represent the same thing in the some other basis, let's suppose P, then I need to multiply by P, right? So if I want to find out this, then I will be multiplying by the P transpose. Okay. So you can multiply by the P transpose. So for example, okay. So if P is this matrix, right? So let's suppose P is this matrix. You can first convert that to the basis of P by multiplying the P transpose or P inverse basically. But here the P inverse and P transpose are same. So it will be it will be P is this, then P transpose you can find out, right? And then if you convert, then there will be X in the basis of P will be P transpose into X. And if I do it, okay, you will be getting something like this. Okay, you will be getting something like this. Is this okay to everyone? That P transpose X will be something like this. So basically what we have done till now, they ask us to evaluate this QX for 2 minus 2. I said like instead of, going directly by plugging in the value of 2 minus 2, let me just see this X in the basis of P. Okay. Then I will be getting this particular vector. Then what can I do? Now I can find QX. How? Now I know that to find QX, you can say that you can put this in the basis of P. So basically this vector which is like y instead of x transpose X, I will be having the basis of P by transpose some diagonal matrix which will the diagonal matrix of eigenvalues. So what are the eigenvalues of this um what are the eigenvalues of this matrix A? Okay, 3 and minus 7, right? So 3 and minus 7 you write, and this is 0 and 0. So basically, you will say that if this is 3 and minus 7, then this will be like 3y1 square plus minus 7y2 square, right? Now, if you know in the basis of P, if you know the coordinates which are this, then you can directly do this, right? Okay, so 3y1 square minus 7y2 square. Understood? So basically, what they are saying that if they give you x in some standard basis, then you can also do one thing. You can represent this x in the basis of p, and then you can calculate for qx. Okay, just using this diagonal form where there is no cross product. Okay, there is no cross product terms. So basically, that's what it is written here. Okay, if you do that, then the final answer will be basically 3y1 square minus 7y2 square, 16 only, right? So what we have done, see here, that instead of directly using it, you can directly use it, but we have multiplied this x with p transpose. Okay, so we have multiplied this x with p transpose, then we have got y, then you can do using the y also. Okay, okay, how we have got p transpose x? Because of the change of basis. So basically, you can see that this if x in the standard basis, and if you want to represent this in the basis of p, then you have this relationship, right? Now this xp can be p inverse x, or p inverse and p transpose here are the same. Okay, so p inverse and p transpose here are the same. So xp is nothing but p transpose x, right? So let's do one more example. Maybe you will get to understand more. So what they're saying, find the orthonormal change of variable of the, so orthonormal or the diagonal. Basically, they mean to say that you just find out this is one representation, but can you just represent this in the form of diagonal matrix? Okay. So what you will do, you will take this, you will find out the eigenvalue, you will find out the eigenvectors, right? Uh, now this x1, x2, x3. So you earlier had x1, x2, x3. Okay, so instead of having some x1, x2, x3 and then multiplying this with the p transpose, let me just find out let me just find out by 1, by 2, by 3 by multiplying in the parametric form. So basically p transpose into x1, x2, x3 will be this by 1, by 2, by 3. Okay, so here this by 1, by 2, by 3, if you want to find out, this is just find out using this relationship. Okay, so which means if they give you x, then first find out the y, right? First find out the y, and then use this. Okay, use this particular formulation. So basically, if they give you x, then you can find out the y, and then you can represent it like this, right? So this is just one extra step that we are doing, but ultimately we are getting the diagonal matrix in between. Okay, so if they give you the x, then you can say that, okay, let me just find out the y first using this relationship, right? And then let me represent this q using the diagonal matrix. Okay, so actually these kind of representation are helpful for many things. So that's why like people have this, but I think it is not required to have much analysis on this. So basically there's a geometric interpretation and so on. So if that is required, then we can have some optional class later on, so where we can further see the geometric interpretation of representing this as a diagonal matrix and so on. But for now, like, let's just stick to our mathematics only, that if given any x, if they ask you to represent this in the diagonal form, then you can find out the by using this relationship, and then you can do this, right? Okay. Yeah. So that is all about the quadratic form. Yeah, last part was little tricky, I know. But to be honest, it is since gate D is happening very first time. So actually, I didn't want to leave this particular diagonalization of quadratic form, but I think it is not required. Okay, we just need to know the basics of this, which means actually this is not much required in the machine learning also. So that's why, like, from the machine learning point of view, I'm saying we are not going to use the diagonalization of the quadratic form. Okay, so which means that we with this, it doesn't make this topic important. Okay, at least the diagonalization part, like, we are not going to have the diagonalization in the machine learning. Okay, so so that's why this topic is diagonalization of quadratic form is less important. That's why we just had some interpretation. But otherwise, given a quadratic form, at least you know that how to find out this matrix, right? You can quickly find out this symmetric matrix, and given a symmetric matrix, you can quickly write something like this, right? So that's all we need to know in the quadratic form. Okay, so this covers our discussion on quadratic form. This covers our discussion on the positive definite matrices. So these are the two topics from linear algebra that we have covered today. Okay, now we will be using the positive symmetric definite or PD positive definite matrices in the calculus for the optimization purpose. Okay, so that's all. Thank you so much.